Question 6 from the 2025 National 5 Physics paper from the SQA, and it's from paper 1. An asteroid of mass 25 kilograms is travelling at a speed of 9,200 metres per second. On entering the Earth's atmosphere, the asteroid burns up completely, and the maximum amount of heat energy released is, and we're given the 5 responses. Well, all that kinetic energy must be released into heat, so that's the key point. It's going to be movement energy, it's going to have kinetic energy, and it's going to be changed into heat energy. Now, what is the kinetic energy to begin with? The kinetic energy EK is going to equal to 1/2 times the mass times the speed squared. So we plug in the numbers for that, we get 1/2 times the mass. The mass is going to be 25 kilograms, and we're going to multiply that by 9,200, and we have to square that. Remember, you have to square the speed. So we do that in our calculator. We end up with an answer of 1.058 times 10 to the power 9 joules. So that's the amount of kinetic energy it has, and when it goes into the atmosphere, that kinetic energy will be transferred into heat energy as it burns up. If it's totally burned up, then all that kinetic energy will be transferred to heat. Now, 1.058 times 10 to the power 9, we have to put it into two significant figures, because we've used two significant figures here and 2 there. So therefore, to two significant figures, we have 1.1 times 10 to the power 9 joules to two significant figures. So our response for that is 1.1 times 10 to the power 9 joules, which is response D. Question 7. The speed v of a satellite in orbit around the Earth is given by the relationship v equals the square root of rg. Now we're told that r is the total distance from the centre of the Earth to the satellite in metres, and g is the gravitational field strength at the location of the satellite, and it's measured in newtons per kilogram. And here's the data. The radius of the Earth is 6.4 times 10 to the power 6 metres. The height of the satellite above the surface of the Earth is 3.6 times 10 to the power 7 metres, and the gravitational field strength at that point, at that height, is 0.22 newtons per kilogram. And we asked to find the speed of that satellite. Okay, let's have a look at the diagram. That's a kind of diagram there, not drawn to scale, but you can see we've got the radius of the Earth here, so we'll put the radius of the Earth in. That's that distance from here to here, and that's a distance of 6.4 times 10 to the power 6. So 6.4 times 10 to the power 6 metres. That's the radius of the Earth. How high is the satellite up? The satellite is 3.6. Now, as I say, it's not drawn to scale. 3.6 times 10 to the power 7. I'm only doing this to show you how we find the total height. So therefore, the r is going to be 3.6 plus the 6.4. So r, the total distance from here to there, is going to be 3.6 times 10 to the power 7 plus 6.4 times 10 to the power 6. And that's going to give us an answer of 4.24 times 10 to the power 7 metres. So that's the total distance from the centre of the Earth up to the satellite. Remember, it is not to scale. I haven't drawn it to scale here. Now we've got r, we can plug r into the relationship to find what v is if we know what g is. So we know that the speed v of the satellite is the square root of r times g, and that's going to be equal to the square root of r, which we just calculated, 4.24 times 10 to the power 7, and we have to multiply that by g and that particular height, which is 0.22. So if we do that in our calculators, we get an answer of 3054, and that's going to be metres per second. Now remember, we're dealing with two significant figures here, so we have to put this to two significant figures. So 3054 becomes, well, that 4 is bigger than just slightly less than 5, which means it's tipping over the 5, so we're going to have 3100 metres per second to two significant figures. So what response is that going to give us? It's going to be response C, 3100 metres per second. Question 8. The weight of an astronaut on Earth is 710 newtons, and we're asked to find the weight of the astronaut on Mars. Well, we do know that the weight of an astronaut is given the following relationship. Weight equals the mass of the astronaut times the gravitational field strength. So we can find the mass of the astronaut on the Earth, because the mass of the astronaut is simply the weight divided by the gravitational field strength on the Earth. And therefore we know that the mass is going to be equal to the weight, 710 newtons, and divide that by the gravitational field strength of the Earth, which is 9.8 newtons per kilogram. So we've got the mass of the astronaut. He comes out to be 72.44, and we'll keep that figure at the moment, kilograms. Now, when he goes to Mars, he's going to have the same mass, but there's going to be a different gravitational field strength on the surface of Mars. So we have to look that up in the relationship sheet, and there it is there, highlighted. Mars has got a gravitational field strength of 3.7. So all we have to do now then is just calculate the weight of the astronaut on Mars. And the weight of the astronaut, W, is equal to mg, same relationship, and it's going to be equal to the mass of the astronaut, which is 72.44, and multiplied by the gravitational field strength of 3.7. Now we do that in our calculators, we get an answer of 268 newtons. So that's what the astronaut is going to weigh on the planet Mars. Now, put that into the following. We have got two significant figures, so we have to put this into two significant figures. So the 8 will round up to 7, so our final answer is going to be 270 newtons to two significant figures. And that's going to give us a response of 270, which is response C. Question 9. Sirius is the brightest star in the night sky. The distance from Earth to Sirius is 8.6 light years. Remember, a light year is a measure of distance, and this distance is equivalent to, and we're given the 5 responses here. So our first thing we have to do is to establish what 1 light year is, and it's not going to be in the data or relationship sheet, so we have to work it out from scratch and then multiply it by the 8.6. So our first calculation is to work out what 1 light year is in terms of meters, and 1 light year is the distance that light travels in 1 full year. So let's work this out then. So distance d is equal to the speed times the time, and we know the distance d is equal to the speed of light, so it's going to be 3 times 10 to the power 8, and we're going to write that as meters per second, like that. Now that's going to be a time of 1 year, so we have to put down 1 year, but it's not in the proper units, so we have to change 1 year into days. So we have got 1 year is the same as saying 365.25, and it's going to be days per year. Then we have to change the days into hours, so we have to multiply by 24, and we know that's going to be 24 hours in 1 day, 24 hours per day. We have then to change the hours into minutes, so it's going to be multiplied by 60, and it's going to be, in fact, in this case, minutes per hour. And finally, we have to change that minute into seconds. It's going to be 60, and it's going to be seconds per minute. Now all the units should cancel out now, so we have got minutes cancelling out with minutes, hours cancelling out with hours, days cancelling out with days, years cancelling out with years, and we have got the following. We have got seconds here cancelling out with seconds there, so we're left with meters. So all we have to do is multiply those numbers together. 3 times 10 to the power 8 times 1 times 365.25 times 24 times 60 times 60. And the answer we get on our calculator is this long number here, 9.467, and it's going to be 28 times 10 to the power 15 meters. So that is the distance which light travels in 1 year in terms of meters. Now we've got 8.6 light years, so therefore the distance to Sirius, the distance to the star Sirius, has got to be equal to 8.6 times that. So 8.6 times this number here, 9.46728. You can keep that number in your calculator when you're doing this, times 10 to the power 15 meters. And we end up with an answer. The following answer we end up with is an answer of 8.14 times 10 to the power 16 meters. Now, if we put that into two significant figures, we're going to get an answer of 8.1 times 10 to the power 16 meters. So that is the distance to Sirius in terms of meters, and the response which we've got here, is 8.1 times 10 to the power 16, is response E. Question 10. The line spectrum from a star is shown along with the line spectra of the elements hydrogen, helium, carbon and nitrogen. And we're asked to decide which elements are present in this star, and we're given the 5 responses there. So there's going to be 2 of those elements definitely in that star. Now you can do that with a ruler on a piece of paper. You can just match up the lines. I've got this kind of like transparent star here which matches up the star, and all I have to do now is just match up the lines in. So let's try out first of all hydrogen, and if we slide down we can see there doesn't seem to be a fit there at all. There's no lines matching up with the hydrogen at all, so we can rule out hydrogen. What about helium? If we slide down, there's that one there's definitely overlapping it, and if we slide up again we can see that those 2 lines here, there's 2 lines here definitely matching, and this line here is matching, and we have got another line which we can slide over here is matching in this position and that position. So helium definitely is one of those elements. What about carbon? If we slide down for carbon we can see that we have got for carbon, there's a couple of lines matching up. There's one line there matching up, there's one line there, and there's one line here kind of matching up. So carbon definitely is an element in that star. Let's try hydrogen. Slide down for hydrogen and you can see we haven't really got any of those lines matching up. We could maybe argue this one here, but it's not the full set. So according to this, it's got to be helium, because helium definitely matches up. You can see that. If you draw your rulers down, I'll match them up like that. Helium's definitely one, and the other one is definitely going to be carbon. Carbon lines up as well. So your response to that one is we're looking for helium and carbon. That's the ones that match up, and that's going to be response C.